Today we are going to talk about section 6.5, and it is on something called tree diagrams. Okay, and this is something useful for multi-step problems with probability. Okay, so just an example, just a very dry example. There are 3 experiments. A, B, and C. Experiment A has 3 outcomes. We'll call them 1, 2, and 3. Experiment B has 2 outcomes. We'll call them A and B. And experiment C also has 2 outcomes. We'll call them C and D. Okay, so this is going to work in the following way. We will perform experiment A. Then, if outcomes 1 or 2 occur, we perform experiment B. If outcome 3, we perform experiment C. So you could think about this as kind of a decision tree. Depending on what the outcome of A is, we run another experiment, but it depends on what A's outcome is. Okay. And the way we want to think about this is the following thing called a tree diagram. So we will have experiment A, and then we have outcome 1. We have outcome 2, which is also possible, and we have outcome 3. After outcome 1, we will perform experiment B, and then we can have either A or B occur, because A and B are the 2 outcomes for experiment B. If outcome 2 occurs with A, we perform B again. And if outcome 3 occurs, instead of performing A or B, we perform C. And the way these diagrams are drawn, what we're going to do is on these arrows, we're going to put the probabilities of each respective outcome. So 50% of the time we get outcome 1, 20% of the time we get outcome 2, and 30% of the time we get outcome 3. And then we're going to record, as we move down the tree, what we record next are not just raw probabilities, but the probability of the outcome based on, conditioned on 1, 2, or 3. So this will be 0.4, 0.6, 0.4, 0.6. In fact, let's change this to make this appropriate, very clear. 0.5, 0.5, 0.7, and 0.3. Okay. So to highlight this specifically, what does this 0.4 mean? This is the probability of outcome A given we have outcome 1 occurring. That's a conditional probability. Which is why we have a different number for outcome A and outcome B, depending on whether outcome 1 or outcome 2 occurred. Okay. So as you move through these tree diagrams, the probabilities are conditional probabilities. Now, of course, if things happen to be independent, then the conditional probabilities are the same as the raw probabilities. But if we have dependence possible, these conditional probabilities will change. So now we want to ask the question, now I'll show you how we compute with these. If we wanted to find out the probability of having outcome 2 and outcome B, this is the probability of the set with 2 intersected with the set with B. And if we switch around the conditional probability equations, we could get this expression. Instead of calculating the probability of B conditioned on 2 occurring, we're going to use that conditional equation, which I'll write down here again, perhaps we've forgotten it. Probability of A given B is the probability of A intersect B divided by probability of B. If we move that probability of B over to the other side, we would get a way to compute the probability of A and B. And that's what we're doing here. We take the probability of outcome 2, which is 0.2, the probability of B given outcome 2, which we see is 0.5. It's this blue circle here. And then 0.2 times 0.5 is going to be 0.1. Okay, so that probability is 0.1. So that's the probability of getting outcome 2 and then outcome B. Okay. So far, this seems kind of useless because these are just mysterious experiments and outcomes that don't matter. The next two examples will be a little bit more salient and help us understand why we might want to go through a process like this. Okay, a box has 5 good light bulbs and 2 defective. Bulbs are selected until a good bulb is found. Find the probability that we only select 1 bulb, 2 bulbs, or 3 bulbs. This is a real world problem, right? So you have a box of light bulbs, you don't know which ones are defective or not because you stupidly didn't throw them away when they were defective because maybe you were scared you weren't supposed to throw them in the trash and thought maybe you'd recycle them someday, and then you just have all these bulbs lying around and you don't know which ones work or don't work. These things happen. Okay, so I think it's pretty easy. What is the probability that we only select 1 bulb? How many good bulbs are there in the box? 5. How many total bulbs are there? 7. So the probability that we select a good bulb right away is 5 over 7. Okay. But now the probability that we only select 2 bulbs. Okay. This is the probability that we select a bad bulb times the probability that we select a good bulb given that the first bulb was bad. Okay, because selecting 2 bulbs means I selected a bad bulb first, then a good bulb second. So that's the probability of 2 events together an intersection, and you can calculate the probability of the intersection of two events by having the probability of one and then multiply it by the probability of the next one conditioned on the first one. That's what we did on the previous problem as well. That was this part right here. Okay, so the probability that we select a bad bulb is 2 out of 7, right? Because there's 2 bad bulbs and 7 total bulbs. Now, what is the probability that we select a good bulb given that the first bulb that we selected was bad? How many good bulbs are in the box still? You can even show me with your fingers. You don't even have to speak out loud. Oh, you all have 5 fingers. You're right. It's 5. Okay. Now, how many bulbs are left in the box? 6. There's only 6 left. So this is what we have to do to calculate this. So this is going to be 10 over 42. This is equal to 5 over 21. Okay. Now we want the probability. We have to select 3 bulbs. So this is going to be the probability of first a bad bulb times the probability of another bad bulb given the first bulb was bad times, again, the probability of a good bulb given that the first 2. So the probability of a bad bulb, again, is 2 out of 7. The probability of a bad bulb the second time is 1 out of 6, because there's only 1 bad bulb remaining and there's 6 bulbs left in the box. And then what's the probability that you pick a good bulb with the third pick? Are there any bad bulbs left? No, they're gone. So that probability is 1. So this is 2 over 42, or 1 out of 21. Okay. And this is equal to 15 out of 21. And you'll see that these three probabilities that we've computed add up to 1, as they need to. Because the most number of bulbs you'd have to select to find a good bulb is 3. So the probability that you need to select 4 bulbs till you find a good one is 0. And same for 5, 6, and 7. Okay, so we talked about a tree diagram here. So we'll draw a tree diagram for this problem. Experiment 1 is taking the first bulb out of the box. And the probability of selecting a good bulb is 5 out of 7. And the probability of selecting a bad bulb is 2 out of 7. Now, if we found the good bulb, we're done with our experiment. The lamp works and we don't care about light bulbs anymore. But if we select a bad bulb, we have to continue on. And once we select the second bulb, it's either good or bad. And now it's more likely now that we find a good bulb because it's 5/6 of a chance, because there's 6 bulbs remaining and 5 good bulbs. And bad bulbs now, it's only 1 out of 6 are bad. And then the third choice, if we happen to get 2 bad bulbs, the third choice has probability 1 for a good bulb and 0 for a bad bulb, because there are no more bad bulbs left in the box. So that's the tree diagram that kind of, like this is a little less writing than what we did before, right? So this tree diagram can kind of help us work our way through a problem and calculate some probabilities. Okay? I think it's easier. And then to find the probability of a given outcome, say this one here, you just follow its probability on the tree and you multiply the numbers together. Any questions about this problem? Okay, this third one is the most interesting, application of these sorts of ideas. Okay, so suppose that the skin test for tuberculosis has the following characteristics. One, if someone actually has TB, it's a 98% chance of getting a positive result for the test and a 2% chance of getting a negative. So that would be, the 2% would be what's called a false negative test. The test came out negative, but the person still has tuberculosis. Now, if someone does not have TB, you have a 99% negative test and a 1% positive test. So, if you don't have TB, even if you don't have TB, 1 out of 100 people who don't have TB will get a positive test result from this TB test for whatever specific reason. And so now what we want to do, well, and then we have this following background rate. Okay, and in general, in the population, 2 per 10,000 people actually have tuberculosis. Okay. Now, here's the problem here's the question we have. Okay, suppose a person tests positive for TB. What is the chance they actually have tuberculosis? Okay, this is a difficult question. Right? Suppose we have a positive test. What is the actual chance that that person has tuberculosis? And we're going to draw a tree diagram to figure this out. So one part of this diagram is going to be actual situation, and the other part is going to be test result. Okay, so the actual situation could be that someone has TB or does not have TB. Then each of these people gets tested, and they could have a positive result or a negative result. Those are the possibilities for the test result. Okay, now we fill in the probabilities. The probability that someone actually has TB is 0.02, 2 per 10,000. The probability that someone does not have TB is 0.998. So 99.8% of the people in the population do not have TB. Okay. So now let's look at the test results. Okay, the first bullet point above says what happens when someone has TB. So this would be 0.98, get a positive test result, 0.02, get a negative test result. And then now for not having TB, 0.01 get a positive test result, and 0.99 get a negative test result. Okay, so now we can do multiplication to figure out various probabilities over here. I'm going to multiply these numbers that I'm going to write down here are given by multiplying the number on the left versus the number on the right in the corresponding part of the result. So this is 0.000196, 0.000004, 0.009998, and 0.989802. Okay. So this is the probability, this first one is the probability that someone has TB and a positive test. This is the probability that someone has TB and a negative test. This one is the probability that someone does not have TB and gets a positive test. And this one is the probability that someone does not have TB and gets a negative test. Okay? 99% of the people are in that last category. Right? 98.98% of the people, 9,898 out of 10,000 are in that last category. The vast majority of people are in that last category. So now we need to calculate, we are told to calculate, suppose a person tests positive for TB, what is the chance they actually have TB? So we want to find out the probability that they actually have TB given that they test positive. Okay, so this is conditional probability. So to calculate that, we have to calculate the probability that they have TB and a positive test divided by the probability of that positive test. Okay, TB and a positive test we see is 0.000196 from looking at the above chart, at that tree diagram. But the probability of having a positive test, to get that we have to sum two probabilities. We have to sum this probability and this probability. Because those are the positive test totals. So positive tests are not very likely at all. And so we sum these two numbers for the denominator. So that's the calculation we do. When we get this, we get 0.02. So, of the people that test positive for tuberculosis, only 2% of them actually have tuberculosis. Okay, the test is not perfect. And since it's very rare to have tuberculosis, it's more likely that you don't have TB and you got a positive test than that you have TB and had a positive test. Okay, these are kind of counterintuitive things. But if you want to understand medical science, you have to be able to understand probabilities like this and situations like this. Caleb.
So where did, why did you use those two numbers on the bottom?
Okay, because I want the total probability of there being a positive test. So looking up at my chart, these four things that I'm about to circle here, these four things are all the possibilities that can possibly occur. Every possibility is contained in those four things. And so if I want to find the total probability of a positive test, since these four things are mutually exclusive, I can add the probabilities of the ones that add up to being all of the positive tests. If there's a positive test, there's two possibilities. The person has TB or the person does not have TB. And since these four events, TB and positive test, TB and negative test, not TB and positive test, not TB and negative test, those four events are mutually exclusive. Only one of those four can occur. and they add up to all total possibilities, I can just add those possibilities there to find the probability of having a positive test. Does that answer your question?
I'm just confused
Yeah.
why 0.000004 is there whenever that was the
Oh,
negative.
it shouldn't be there. That's why. Because I wrote down the wrong number. So I can see why that would be confusing. That's what we wanted to write down. Yeah, that's the, okay, thank you. As we see, mistakes occur. We get bad test results. We write down wrong numbers. Thank you, Kayla. Other questions about this example? Okay, there's some special words that go associated with this. I'm not going to ask you to know these words on an exam, okay? But you might need to have these words when you're doing the homework problem. Okay, so let me write these definitions. The sensitivity of a medical test is the probability of a positive result in the presence of an infection. So for the problem we just did, the sensitivity of the TB test is 98%, because 98% of the people that have TB will get a positive test result. So that's the sensitivity. The specificity of a test is the probability of a negative test in the absence of a condition. So here the specificity is 99%, because 99% of the people who do not have TB test negative. So that's specificity. Okay. The positive predictive value which is often abbreviated, as one can imagine, as PPV, is the probability of having the condition given a positive result. So that number we saw there, that 2% that we just calculated, that's the positive predictive value of the tuberculosis test, according to this problem. And then the negative predictive value, NPV, is the probability of not having the condition given a negative test result. That is not something we calculated for this problem, but we can do it now. So let's calculate the NPV. This is the probability of no TB given a negative test result. Probability of not having the condition given a negative test result. So this is going to be the probability of having no TB and a negative test divided by the probability of a negative test. And you can't see those numbers anymore, they're gone, but perhaps you can see them on your sheet of paper. The probability of no TB and a negative test is 0.989802. The probability of TB and a negative test is 0.000004. And then that 989802 comes up again. And this is 0.99999 6. Okay, so the negative predictive value is very good. If you get a negative tuberculosis test, you can be pretty confident that you do not have tuberculosis. If you get a positive tuberculosis test, you should not be confident at all that you have tuberculosis. Okay? These things seem weird, right? Okay, homework. This is section 6.5. 14, 20, 30, 38, 48, and 50. Okay? We've run out of time. I'll have the book open here if you need to get that. And I will see you guys on Friday. There will be a quiz on Friday. It could be on any of the sections in Chapter 6 that we've covered so far. So probability stuff. Thank you.